So, students, last time we discussed about the principle of impulse and momentum, and we introduced the concept of conservation of linear as well as angular momentum. And as an initial application of the principle, we discussed also a problem where we applied the principle of equivalence of the impulse of a force with the change in linear momentum of the system. Now, in today's class, we will be discussing a few more problems here. For example, this present problem taken from the book of Merriam. Here, in this problem, it is saying that a simple pendulum of mass A, Ma, this is the simple pendulum A, and the length L. So, this string length, we can say the equivalent length is L, is suspended from the trolley. This is the trolley of mass mb. So this is the trolley B of mass mb. This mass is being given, and the mass of the bob of the pendulum is mentioned to be equal to ma. Now what it is saying, that if the system is released from the condition of rest at theta equal to 0 position, that means when this pendulum was at the horizontal position as marked by position 1 here, we have to, and the entire system is released from the condition of rest, we have to determine the velocity of the trolley. That means what would be the velocity of this trolley when theta becomes equal to 90 degree. That means when the pendulum will swing and it occupies this vertical position, which is marked by 2 here. So at that position, when the pendulum comes, once released from this condition of rest from this position, what would be the velocity of this trolley that we have to find out. So what we see from here is that, here it will be block B. So let me just correct it. This will be block B and this will be block A. So we just rectify this one. So this is velocity of the pendulum A and this is the block B. And here it is also mentioned that the friction is negligible. So what we see, that in this case we note, that means if we draw the free body diagram of the system, we see that these are your forces which are acting. These are the combined support reactions offered by these two rollers, and these are the self weights of the whole thing. So if I suppose that this vertical direction as the y-axis and the horizontal direction, if we take it as the x-axis, we note that if there is no friction that is present in this trolley system, there is no net force which is acting along the x direction. So since there is no net force acting in the x direction, we can say that the total linear momentum of the system along the x direction is going to be conserved. So since initially the entire system is at condition of rest, and if we suppose that the velocity of the ball or the pendulum, whatever, be VA, this is actually a printing mistake, this should be VA and this should be VB. So let us just say that this will be this will be VA, and the block B, this will be velocity of will be VB, and this one will be this one will be block B or the trolley B. So therefore, since initially the entire system is at the condition of rest, and if we suppose that the velocity of this pendulum ball or bob will be VA when it reaches the position at theta equal to 90 degree. And at that time, let us consider the velocity of the trolley B, both positive in the x direction. We assume both of them to be positive, and we say that this is VB. Now we have to remember the fact that this will be the velocity. This will be the velocity that will be seen from an observer who is standing in the trolley. So that he will see that this will be its velocity, obviously. So the actual velocity of this bob is therefore going to be this. We can take it to be the relative velocity, because this velocity is being measured by an observer who is standing in the trolley here. Suppose a person who is standing in the trolley, he or she will record this velocity. So the absolute velocity of this bob or the ball should be equal to the relative velocity plus observer velocity. So it should be therefore VA plus VB. This we need to remember, that when we are going to apply the principle of impulse and momentum, or from there the hypothesis or corollary that we have the conservation of linear momentum, we have to remember one thing, that all velocities should be the absolute velocity. There will be no relative velocity term that will be included into our system. So therefore, by taking actually the absolute velocities, we can say that summation gx is going to be constant. So we can therefore say the total momentum initially of the system was 0, because everything was at condition of rest when I release this system from the position 1. And therefore, the total momentum of the system will imply the momentum of this block, which should be mb into vb. So there is some mistake here. So it should be mb into vb. We can write this must be mb into vb. And then we have, this is your, the block A. So this is ma, that is the momentum, a mass of the block A, into its absolute velocity, and its absolute velocity is obviously VA plus VB. So therefore, we can write that if we write the summation gx equal to constant, that means if we assume that the total linear momentum of the system in the x direction is going to be constant, so we can say therefore that mb into vb, that means the linear momentum of this block when the entire configuration reaches the position 2, that is the momentum of the block wheel, we can say, plus this being the absolute velocity of block of the ball A. So this is the absolute velocity of the ball A, and we can write that ma into va plus vb is going to be 0. Now my objective here is to find out this velocity Vb. In that sense, we can say that both these velocities, I mean to say Va and Vb, they are unknown to me. So I have two unknowns, but I require one more, but we just have only one equation from the conservation of linear momentum. So we require the second equation, and the second equation is obvious. What is that? We note that there is no friction, it is being given. So, and also we note that there are no other forces, active forces other than gravity, which is present in the system. See, these normal reactions are not active forces, correct? So only we have these gravity forces that is present in the system. So in absence of friction, right, we can therefore say, or so to say, that there are no conservative forces which are present in the system. We can say therefore in this total case, the total energy of the system is going to be, total mechanical energy of the entire system is going to be conserved. So therefore we can write the conservation of energy equation between the two states. We can take this state 1 as the initial state, and this is state 2, which is, we can call it as to be the final state. And since we are going to apply the principle of mechanical energy conservation, so I assume that this horizontal line which was initially there, we define this to be our datum. So everything in the downward direction is taken to be negative. So therefore, what we do, we apply the principle of conservation of total mechanical energy between these two states. And again, we should remember, when we are going to apply the conservation of energy equation, we should remember that we need to deal with all absolute velocity terms. So therefore, if we just go and write this position, we can say that T2 plus Vg2 is going to be equal to T1 plus Vg1, and therefore we can say the total mechanical energy of my trolley B will be given by, this will be your M, we can write that this will be MB into VB square, right, plus this will be the total, the kinetic energy. This represents the kinetic energy. This total kinetic energy should be equal to your we know that this is MA, so it should be MA half MA into VA plus VB whole square, and therefore this must be, we can say that we can say that this will be, therefore it consists of only the potential energy of the bob. So we can take that this will be equal to MA into GL. So we can say T2, that is going to be the total kinetic energy of the system, since we have two particles here. Assuming that the trolley is a particle, the bob of the pendulum is another particle. So we just apply the principle of energy. That means actually this here represents summation. That means we should have put this sigma sign here in front of it, sigma. And here as well we need to put this. So let us better write this sigma sign, because this is going to be applicable. We are writing it for the system of particles. Here we have only two particles. So this is, this is written like this. We can put the subscript I, and can say this is I from 1 to 2. That means there are only two particles. However, the motion of the particles are connected with each other, and we say that this is going to be my total conservation of mechanical energy. So it will be therefore half MB VB square plus half MA whole into VA plus VB whole square, minus it is going to be MA into GL, because this is minus, because we are in the downside of the datum line. If you recall that the datum line is here, so anything in the downward direction is to be considered as positive, a negative, sorry, and anything in the upward direction is to be considered as positive. And on this line, that means here the Vg should be equal to 0. The potential, gravitational potential energy is taken to be equal to 0. So quite naturally, therefore, we can write that this is going to be my equation. This is T1 plus Vg1, since both of them are initially at condition of rest, so we don't have any total kinetic energy in the condition 1 or in situation 1 or in the initial condition, plus the total gravitational potential energy, because that line we have chosen as to be our datum line is going to be 0. So this side should be equal to 0. So we can therefore say that it is going to be that we can write from the above equation that it is MB into VB square plus it is MA into VA plus VB is going to be equal to 2 into MA into GL. So this is now going to be my second equation. So now we have two equations at our disposal, and we see that our desired unknown is VB. So what I do from equation 1, I can say that, so we can say that equation 1, sorry. So we can say from here that just we add a page. So we can say from here that this is our equation 1. So from equation 1, I can say that VA, because VB is my desired unknown, so I need to replace VA. So I say that VA is going to be equal to minus, this is MA plus, we can write this is going to be MA plus MB into, we can say that this is MA plus MB into divided by, sorry, this will be divided by MA, this will be divided by MA into, this will be going to be equal to VB. So you see that there is a negative sign that is present in the system. What it means is that the velocity of the block and the pendulum, the relative velocity of the pendulum bob and the carriage, the velocity of this carriage, that means VA and VB, right? This is VA and this is VB. So they are having a negative sign in present in between them. So it indicates that if this is going to be positive, in fact it is going to be positive, obviously, then the trolley will be, you know, it will, its velocity will is shown here tentatively in the positive x direction, but actually the motion of this trolley will be in the opposite direction. That means the bob is having the velocity towards left, so it means that the carriage will move towards right. This negativity between the two velocities must be there because it has to balance the initial momentum, and since your initial momentum was 0, so you know, therefore they have to be have a negative sign in between them. So once I see from here this equation, now we can come back to our equation 2 and can manage it this way, because we need to actually replace this VA term from here. So we can therefore say we can just put this VA term into this equation and can write. So now from equation 2 we can say, from 2 we can write, from 2 we can therefore say that it will be MB into VB square. So we can say this VB square, we can take it as a common and can write like this, that it is going to be MB, of course, and then you see here it is VA plus VB. So actually I just produced this one. This VA plus VB essentially indicates what? So it indicates minus MA plus MB by MA, right? And in place of this I am putting, so I can take this plus 1 into VB. So we can write it in this manner. So obviously then this will indicate what? So this will indicate minus, we see this is MB by MA, because this one MA and one MA is getting cancelled. So it is minus MB by MA into VB. So that is going to be my absolute velocity of the block of the pendulum bob. So it is minus MB by MA into VB. So since we require this term here, so I can therefore say that it is going to be MA into this, we can say that it is going to be MB by MA whole square. So we can say this is MB by MA whole square, correct? This into VB square, because there is this VB term. So here it will be VB square and then this VB square. So I can take the VB square common and can write it in this manner. And that should be equal to here, this is twice MA into G into L. So ultimately what we can therefore say from here, we can write from here that VB square, that means our desired velocity that we are going to write, is equal to, we can say this is twice MA into GL divided by, it will be, we see that this is MB plus, this will be MB square divided by MA square. So we have, this is MA, and I can write it this manner. So I can just segregate this equation. In this case, we can say this is twice GL, and this non-dimensional term that we can write, it will be, this is, we can say this is MA, and then we can write this is MB square by MA. Or what we can do from here, we can take this MB also common. So we can write this in this format. So by taking this MA and by taking the MB common from the denominator, we can say that it will be MA by MB. This is taking common. So this becomes a non-dimensional term then. And then it becomes 1 by MA by MB. We have taken this MB common from here. So we can write it in this manner decently. In a decent way, we can say that it should be 1 divided by 1 plus this, we can say that it will be MB by MA, because we have taken MB common from here. So it will become MB divided by MA into, this will become root over 2GL. So we can say actually the velocity dimension is coming in this 2GL term, right? Because this is acceleration and this being the length. So root over 2GL will give us the, sorry, it's not root over because we have not taken the root yet. So 2GL. So therefore this is going to be my equation. Now from here I can therefore say that the VB, that means our desired velocity of the trolley, turns out to be as root over 2GL, and this will give me the dimension of the velocity. Under root, we can say that it is the ratio of these two masses, MA by MB, divided by, it is 1 plus, this is going to be MB by MA. MB by MA. So we can write it in this manner. So this is going to be my answer in this form. Let us go and check the answer provided in the book. This problem is taken from the book of Merriam and Craig. So it is 3 by 213. So quickly just going to the answer section, we can cross check whether we are able to write it in a proper manner or not. Or there is some other alternative, the format of the answer being provided by the author. So let's just cross check it. So since our problem is 3 by 213, so we go quickly. We see that this is, written in this manner. It is MA by MB into root over 2GL divided by 1 plus MA by MB. So we just see it here. So this is the factor, this, I think whether it is correct or not, this is MA by MB. So this is MA by MB. So I think there is some mismatch here. From here, let me check whether it is correct or not. This is MB by MA. So we just check this one. This is going to be this equation. VA is written in this manner. VA is I think here I made a mistake. Is it VA? No, VB. Okay, it is VB there. So MB into VB. This is here also MA into VA plus VB. So it is going to be MA VA. No, it is okay. MA VA divided by MA plus MB. So it is therefore VA plus VB. So we need to add VB here. So therefore it becomes minus MB by MA. This is minus MB by MA into VB. So we can put it here into this equation, half MB VB square. And in place of this, we are going to write, this is MA. So this is MA. This MA is also there here. So this is VB square. That means it becomes 2 into MA into GL divided by, this is going to be MB plus MB square by MA. Okay, fine. So from here we have taken the MB common, and once we have written this equation, we write this equation in this manner. Okay, so I think in the book it is mentioned in the other format. So it is MA by MB. So MA by MB is taken from here. Okay, we can write it in this way, because then we will be having the homogeneity in the equation. I mean to say, here it is MA by MB and here it is MB by MA. So in order to eliminate that, what we need to do is MA by MB getting multiplied over. So we can say that this is going to be equal to square root. This is MA by MB whole square divided by, it is 1 plus, this is going to be 1 plus MA by MB, right? So we can write it in this manner. So we can say that, so that the ratio becomes uniform for both the cases, we say that VB is being given by root over 2GL into, we can take the under root expressions common. So we can take this MA by MB whole square, since it is under root, we can take it out from the root sign, can write this is going to be MA by MB. Now this becomes under root by, this is 2GL divided by, this is going to be now 1 plus MA by MB. So we see therefore that the velocity of this carriage, is ultimately expressed as the ratio of these two masses, and it is, seen like this. Now in many instances, what we find that the carriage from where the pendulum was suspended, correct, that carriage mass is sometimes becomes very heavy in comparison to the mass of the pendulum bob. So it means that your MA by MB, this ratio is going to be, this is going to be equal to almost 0 if your MB is very large. So it is therefore pretty clear that as your MB is, if your MB is much greater than MA, in many cases we can write that, not as, we can say that if we can say that this MB is going to be much greater than MA, that means the carriage is of heavier mass than the pendulum, then obviously we see from here that this ratio, I mean to say MA by MB, this is going to be tending towards 0. So if this is going to be tending towards 0, we say that from the above equation, VB tends to 0. And that is obvious, because if we note that the bob, I mean to say the carriage is of heavier mass in comparison to your pendulum bob, naturally, the motion of the carriage will be negligibly small as the pendulum is allowed to swing. So we see that this is going to be my velocity of the block B, and the sense of this velocity will be obviously towards your left side, towards your right side. Why it is so? Because we have just now seen that there is a negative sign between, you see this equation, there is a negative sign between the velocity of A and B. So it means that if VB is towards left, which is in fact it is, if VA is towards left, which is in fact it is, because the relative velocity of the pendulum bob is always going to be towards this left side, right? So since this velocity is towards the left, and since there is that negative sign is present in the system, so we naturally find that the velocity of block B will be going towards right. So that will be the complete answer to this question, that where we are getting this, this velocity. So this is number one. Number two is that here again, the problem is something like this, that the two convenient configurations have been provided in our question. That means the initial condition was obviously convenient because it was horizontal in nature, but the final position is also conveniently taken as to be the case when theta becomes equal to 90 degree. But just like the other sums, we may be interested to know the velocity of this carriage, correct, as a function of this angle theta, which defines the position of this pendulum as it swings against gravity. Please note that this entire system is in vertical plane, so it means that there is acceleration due to gravity is acting here. So as the pendulum is swinging like that, as this theta defining as its coordinate, that means theta will define the position of this pendulum bob in the vertical plane, and we will be interested to know how this trolley velocity, right, assuming that these two masses are comparable. That means the mass of block B is not much greater than the mass of block A. I mean to say the pendulum mass A. So MA. So if these two masses, I mean to say MA and MB are comparable to each other, right? One is not much more than the other or much less than the other. So if the two masses are comparable to each other, we note that we will be interested to see how our this carriage velocity will basically vary with this angular position theta. So I would ask you therefore, students, that as a homework you must solve you must find the expression for the velocity of this carriage as a function of theta, and check that you are getting the result that theta equal to 0, everything should be 0, number 1. And number 2, that means when you are going to put theta equal to 90 degree in your expression that you are going to find, you should get the answer that we have actually arrived at during our solution in this problem. That means in your expression, if I put theta equal to 90 degree, we must be getting this expression as the output. So check this thing, do this sum, find out the carriage velocity and establish a mathematical expression which correlates the velocity of this carriage and the angular position of the pendulum bob in the vertical plane. So this is therefore the another the thing. Another comment on this problem is that speciality of this problem is that this type of problems, as I have already told during our lecture when I introduced the concept of theory of this principle of equivalence of momentum and impulse, I mentioned that there are certain class of problems in dynamics where we can simultaneously apply the principle of conservation of momentum. It can be linear momentum, it can be case of angular momentum, and at the same time we require the to apply the conservation of energy principle also to solve our problem. And at that point of time I mentioned that since the work energy type of problems are most suitable when your forces which are involved, active forces especially, which are involved into your system, are known as the functions of positions, correct? And the principle of impulse and momentum equivalence, they are the two mirror images of each other. Principle of work and energy equivalence and the principle of impulse and momentum equivalence, they are the two mirror images of a problem of mechanics. And we know that if we are going to apply the principle of conservation of principle of equivalence of impulse and momentum, we know that the force fields or the different forces, or maybe some of them at least, should be known as the functions of time, And if all the forces are not known as functions of time, then the remaining forces which are not mentioned as functions of time, they must be constant. Only when we can apply the principle of the equivalence of impulse and momentum to solve such problems of dynamics. However, when in your system all the forces mentioned are being given as the functions of are being given as constants. For example, in this case, you see here, these are your constant forces, correct? So if these forces are going to be constant, of course, we can say that we can apply both these powerful principles of mechanics as an alternative method of the Newton's second law of equation. They are derived from the second law of equation. If you recall, both the principle of equivalence of work and energy as well as the principle of equivalence of impulse and momentum, both these powerful principles have been derived using the Newton's second law of motion, right? So we are not actually, defying Newton's second law of motion. We don't have any scope. When we are studying Newtonian mechanics, the basic principle is based on, the Newton's principles. So we cannot defy it. So that was actually the fundamental principle. And from there, we derive two offshoots. These two are the offshoots of Newton's second law of motion and can serve as an useful alternative to some of the special types of problems like this one. So here we see, therefore, now these types of problems or this class of problems of dynamics, they constitute a very powerful, the problems or important problems. But again, students, I like to mention that it is to be remembered very carefully that whatever velocity terms that we are going to use in these two principles, I mean to say the principle of work and energy and the principle of impulse and momentum equivalence, whatever velocities that we have been using in these two methods or in these two equations, they have to be absolute velocities or the velocities as recorded from an inertial reference frame. So I think you have understood this problem, and I will ask you to solve few such problems from any standard textbook in order to have a control on these powerful concepts. Now, with this introduction to this problem, now let us move on to our next problem. So our next problem is also taken from the book of Merriam and Craig, and this is going to be our next example. So this problem is problem number 3/227 that we have taken from this book of Merriam. What it is saying is something like this. Let us go and explain the problem and its figure. So this is your problem and problem statement and the problem figure. So we see that it is being given the 6 kg sphere. So you see this is the sphere which is 6 kg. Again, here multiple mass points are there. So again, we are not dealing with a single particle. We deal with a multiple particles, system of particles, but their motions are dependent on each other. But as I said that in the next chapter, when we will formally take up the dynamics of the group of particles, there the particles motion may not be dependent on each other. They can be independent of each other, of course. However, in this case, it is said that the 6 kg sphere, so this is the 6 kg sphere, and the 4 kg block, so this is the 4 kg block shown in section. This is the sectional view, so that's why it is said that shown in section, are secured to the arm of negligible mass which rotates in the vertical plane about a horizontal axis. So this entire thing is again in the vertical plane, correct? So it is mentioned that these two are connected to a light rod of negligible mass. This is arm, and it is being pivoted here, and the axis of rotation, of course, is in the horizontal direction, or in our case the axis of rotation is perpendicular to the plane of our screen or khata. Now it is rotating about this horizontal axis, and therefore it offers the negligible resistance towards the rotation. Now the 2 kg plug, this is a 2 kg plug, it is being released from the condition of rest at A. So when it is here at this point A, you see the velocity of this is going to be equal to 0. Okay? And it falls into the recess in the block when the arm has reached this horizontal position. So the motion of this one and this one are synchronized. Synchronized in the sense that when it is rotating in the counterclockwise direction as seen from the front, we see when it comes to this horizontal position, right? That means this angle, when it is going to be equal to 0, at that particular situation, this one is coming and getting hit into this and getting fit into this recess. So it comes and goes into the recess and gets plugged with each other. Now, an instant before the engagement, that means when this arm has come to this horizontal position, right? When this arm has come to this horizontal position, because then only the engagement between this the plug and if you can call it as a socket, then the plug and socket, this engagement basically takes place when this entire lever it becomes horizontal. So an instant before engagement, so this is we can consider this horizontal position. We can consider that this serves the purpose the instant before engagement. So it is just before engagement. We can write this is the situation just before engagement, and when actually the engagement takes place, there is a tremendous the forces which are generated between the socket and the plug, because obviously you see the plug is falling and the socket is coming. So the socket and plug, when they get plugged with each other, jammed with each other, at that point of time there is a tremendous force of interaction between them is acting. Now such forces are termed as the impulsive forces. The impulsive forces. So we can say that such forces, we can call them as the impulsive forces. And the characteristic of the impulsive force is that it has got a huge magnitude, but it acts for a very short duration of time. That means if we draw a graph showing how your impulsive forces varies with time, so if this is going to be my time axis and if this is going to be my impulsive force plot, I show the impulsive force by putting a tilde sign on the top. So it is F tilde. It indicates that it is an impulsive force. Then the graph of such impulsive force is going to be, we can, if we draw this variation, then the graph will be something like this. So this will be going to be the graph. It is having very large magnitude. In fact, it is undefined. The magnitude is very large, right? And the act of the duration, or the duration during which this force will be acting, so this time gap, so if you can say that this is the time gap, this time gap, if we call it epsilon, then this epsilon is tending towards 0. However, the thing is such that the total impulse created by this impulsive force, that means the area under this small strip, this is going to be constant. And I can call that this is giving me a definitive impulse. So I can say this is I tilde. The area can be written as I tilde, and the magnitude of this becomes the magnitude of the force. That means your F tilde. This is your F tilde. The magnitude of the force F tilde is going to be very high because your epsilon is going to be equal to 0. And this is I tilde, we should not, I do not put the tilde sign on top of it, just to indicate that it is giving me a moderate magnitude of the impulse. So although the magnitude of the force is very large, but since it acts for a very short duration of time, it is therefore able to impart an finite impulse on the system. And normally this impulse is very large compared to the other non-impulsive forces. Maybe the other, maybe a non-impulsive force, say the force due to gravity, can be, represented by a flat line like this. So you can therefore jolly well understand that if there is any non-impulsive force or any general category force, for such a small duration of time, the impulse that will be provided by that non-impulsive force will be very, very small compared to the impulse provided by the impulsive forces. So therefore, it is a general rule that if in your system there are mixed type of forces, that means you have non-impulsive force, say you have non-impulsive force, as well as you have the impulsive force, correct? So if these two are there in a particular system, if both these two categories of forces are present, it is customary that we should take the impulse of these non-impulsive forces is therefore customarily taken to be equal to 0, right? That means we need not consider the non-impulsive forces for calculation of impulse when there is associated with the system. Along with these non-impulsive forces, there are impulsive forces also present in the system. So when you are actually calculating the impulses of both, then you may ignore, at least actually it is imperative that you have to ignore the impulse created by such non-impulsive forces. What are the examples of non-impulsive forces? Obviously, self weight of any system, correct? Spring force, springs are not able to take any impulsive forces. So spring force, all they come under the category of non-impulsive forces. So you have to be therefore careful little bit if in your system there is any chance of impulsive forces like this here, because whenever there is a collision, this is actually called as a collision. This is called perfectly elastic collision, as you have studied in your fundamental physics course in your school days. So you see that whenever such kinds of collision, right, or impact between several systems occur in a system, and that constitutes any spring force or the gravity force, please note, while calculating the impulse of such impulsive forces, we have to neglect the impulse of such non-impulsive forces. Anyway, so you see, we were discussing this particular thing in connection with this engagement, and we defined this line to be just before engagement. At the same time, that is very important, at the same time, this also indicates the situation just after the engagement, just after engagement. So the same position. Why it is so? Because when there is an impulsive force acting into system for such a small duration of time, it will provide an infinitely large acceleration. There is no doubt about it, because your force is very, very large. So it produces momentarily an impulsive acceleration into your system. However, since this time gap is very small, the displacement during this time, epsilon, you see, this displacement will be, if we assume that the acceleration is essentially constant, in this case we can say delta x, assuming that our system is initially having motion or maybe at condition of rest. We see that doesn't matter actually the initial condition. We see that it is half a tilde into epsilon square, correct? So this is going to be my displacement, like half a t square. So you see, since your epsilon is very, very small, you see this quantity will also be tending towards 0. So that therefore explains that when there is this kind of, the momentarily large situation of momentarily large generation of forces like impulsive forces, we see that during that time the displacement of the associated system is actually, there is no displacement between them. So therefore we can therefore say that the same line can indicate the two different positions, because just before engagement and just after engagement is actually this time gap epsilon, during which our this impulsive force actually acts. Correct? So within this time gap of epsilon, essentially there is no change in the configuration, and the same horizontal line I can treat it just before engagement and just after engagement situation. And you know from your knowledge of school days physics that when such collisions take place, except for perfectly elastic collision, we see that the energy is not conserved. That means here during this process we don't have any conservation of energy. In fact, there will be a loss of energy into your system. Correct? And we can also see how that loss of energy we can measure. However, just after engagement, if we now consider the situation post-engagement situation, we see again, if there are no other non-conservative forces present in your system, we'll see that again energy is going to be conserved. But during this small time epsilon, this time phase, we see the energy is not going to be conserved. So what we have been asking in this question, now we are asked to find out the angular velocity omega of the arm, right, immediately after the plug has got wedged itself into the block. So this is the thing. That means when this plug is falling down by a distance of 600 millimeter, it comes and reaches this horizontal position. At that same time, this entire assembly is rotated. Omega 0 is being given. The initial angular velocity of this system is being given to be 2 radian per second. And at that same time, when the plug has come to this position, at the same time, this entire system attains the horizontal configuration, and we do not take into account the differences in heights and sizes and shapes. Imagine all of them are particles, and we see that they get engaged to each other, and we have been asked to find out what is the angular velocity of the entire assembly just after this kind of engagement takes place. So this is our system, and you know that we can therefore say that this block, this plug, when it is coming and just just before engagement, so we express just before engagement, we express it with the blue line, and immediately after engagement we write them in the green line. So if we suppose that, so we can say that just before engagement, I can say the plug's velocity will be equal to how much? So we can say the plug, I can call this as I can call this as the number 1, and this assembly, I mean to say this sphere and this socket, this entire assembly along with the massless rod, we take this as our particle number 2. So exactly therefore V1, that means the velocity of the particle number 1 just immediately before the engagement is calculated to be equal to how much? Since it is freely falling through this position, so it is going to be 2gh. That means in this case, this is going to be 2 into 9.81 meter per second square, and h being equal to 0.6, so much of meter per second. So we can use the calculator slowly to calculate the thing. 2 into 9.81 is obviously 19.62. That is your this thing. that multiplied by 0.6 will give me this value, and if we take the square root, this comes out to be 3.431 meter per second. So we can therefore say that this velocity is 3.431 meter per second. So that is the velocity with which it is coming, and you know that we can express this velocity with this arrow, blue arrow. So this is going to be my velocity v1 just before the engagement. And just after engagement, of course, if we assume that our angular velocity just after engagement, everything is expressed with the the green pen. So if we suppose that just after, and I just paint this arrow with a blue pen because this is representing just before engagement. So we see that if this is the thing, if we suppose that the angular velocity just after engagement, if we call this as omega, then we can see from here that at the this omega is there, we can write this as omega. So we find that when this thing comes here, we see that every entire assembly, because your plug has also becoming the part of the system, it is now the integral part of the system. So we note that here the entire assembly will be rotating with this angular velocity of omega radian per second. So if that since there are no forces other than the force due to gravity etc are acting, right, and we see that we can of course we note that in this position we can calculate the forces which are generated here, and since you know that here the self weight etc are there, and of course we know that this is an impulsive kind of thing, impulsive force, and we know that when we are taking into account these impulsive forces, we can of course ignore the presence of the non-impulsive forces here. The non-impulsive forces obviously are the self weights of the system. So since you know that this system is there, we can actually carry out the what is termed as the principle of conservation of angular momentum. Why it is so? It is because that right now we have considered that we can neglect all your non-impulsive forces, and here the non-impulsive forces of course will be the forces due to gravity. So since we are ignoring it, so I therefore see that here there are no other things which are acting into your system, and therefore we can say that about the point O, that means about the axis of rotation, about this axis of rotation we can see that about this axis of rotation we can consider that the conservation principle of angular momentum can hold good. So as a result we can say that the angular momentum, we can write it in this manner, that angular momentum HO about the point O is going to be constant. So if this is going to be constant, of course we can see that it indicates that HO2, we can say HO2, it represents the post engagement, is equal to HO1, that is the pre-engagement. The angular momentum before engagement and after engagement, they will be necessarily equal. Now in this case, if I suppose what is going to be my the angular momentum here, we note from here that in situation 2, that means just after the engagement, the entire unit, it is a total unit of the system. So since it is total unit of the system, the angular momentum at point 2 will be equal to what? If we assume that the velocity, angular velocity of the entire system just after engagement, if we take it to be equal to omega, then the angular momentum here will be equal to what? That means when your system has come to this, this position. So it means since it is being rotating, so you see that the angular, the linear velocity of this is going to be in this downward direction, and of course this velocity and this assembly's velocity after engagement, it's going to be in the upward direction. So obviously the angular momentum at point 2, that means when they come here at the final configuration, this we can say, or we can say this is a this we can say as to be one A or B. The situation A, this is immediately just before engagement. We can define this by situation A, and just after engagement we can define it by the situation B. So we can say therefore that HOB and HOA, they must be equal to each other, and we see that HOB is going to be anti-clockwise in the sense because their angular momentums are with respect to point O, definitely is going to be, it is going to be definitely in the anti-clockwise direction. So if that is the case, I can therefore say that the angular momentum here will be this, this is how much? This is going to be omega into 0.3, correct? So that is going to be my angular momentum, the velocity. That multiplied by this mass will give me the linear momentum. So when you are taking the angular momentum, so it means that you are going to take the moment, and the moment is here, this arm is again 0.3 meter. So therefore the angular momentum here is going to be 6 into 0.3 square into omega, correct? So therefore we can write, and since this is after engagement, so I write it in the green pen. So I say that 6 into 0.3 square into omega will be the angular momentum of this block, plus this is, this one, this 4 kg. So we can say 4 into 0.5 square, 4 into 0.5 square into omega, correct? And then we have plus, then you see here, this is how much? This is 2 kg. So the 2 kg and 4 kg, they are in the same position. So I can add this 4 kg and 2 kg together, and actually since they are in the same position, obviously I can write therefore this is 6. 6 is because it is 4 plus 2. This 4 and this 2, because they are assembly now, the entire assembly is 6 kg. So this will be therefore, the thing that we are getting it like this. And we see that here, this is going to be equal to minus. Why it is going to be equal to minus? It is because that, no, not going to be minus, sorry. So we see here, since at this initial position, that means when just before engagement, again, if we notice just before engagement, the angular velocity was omega naught, that was being given. And how much angular velocity it was given? Now it was given to be 2 radian per second. So the angular, and the sense is in the anti-clockwise direction itself. So therefore, angular momentum of this system now becomes equal to how much? I write it in the blue pen because it is just before the engagement. So it is turning out to be as 6 into 0.3 square, correct? Plus we say that it is 4 into 0.5 square, right? This multiplied by omega naught. Omega naught is how much? That is being given to be 2 radian per second. Please note, this is omega naught, that is 2 radian per second. So I put this is 2. So here please note that this is basically your omega naught value. This is your omega naught value. Okay. So and this 6 it is because it is 4 plus 2. 4 plus 2. And then this block, this is also the part of the system immediately before engagement. So that velocity is in the downward direction. We have already calculated this velocity. The velocity has been calculated and it is shown to be in the downward direction. So naturally the angular momentum of this plug, right, just before engagement will be in the clockwise direction, and so we should be having this minus sign. So therefore it will be how much? This will be, this one is having 2 kg, so 2 kg block, so that mass was 2 kg. So we can therefore say it is 2 into this is the moment of the linear momentum. So it will be 2 into 3.41 is the velocity 3.431 into this distance. That means it is 0.5. So we see that in this equation we have only unknown here in this equation is omega. So therefore now I can write, now I have written with different pens because I said that immediately before engagement we will write it in the blue pen. So this is the total system before engagement, and after engagement we are committed to write it in the green pen. So this is before engagement with the sink. Now the rest of the thing we can carry out with our red pen analysis and can therefore say that this is going to be omega, and we can say that this equation is written in this way. This is 6 into 0.3 whole square plus this is 4 into 0.5 square, this into 2, this is into 2, then we need, it is minus 2 into 0.5 means it will be 1 into 3.431 divided by this one will be you see omega taking common, so already it has been taken common, so 6 into 0.3 square. Oh, so we can write it like that. It is both 6 into 0.3 square into 0.5 plus 0.5 square. So we can write it in this manner. So this is going to be my therefore omega, and we need to check the sign of omega. That means whether this is coming out to be minus or plus, something like that. So first I evaluate the numerator part. The numerator part is going to be 6 into 0.3 square. That turns out to be this plus 4 into 0.5 square. So it is like this. So this into 2, this into 2, 3.08, and then it is minus 3.431. So you see already we have a negative sign on the top. That means this is going to be minus 0.351. So we say that it is minus 0.351, right? So this is minus 0.351, and of course this is 0.3 square. So we just check, plus this is 0.5 square. So this multiplied by 6, give us 2.04. So 2.04. So that means this is going to be equal to how much? So we can take the reciprocal and multiply it by 0.351, and the result turns out to be as 0.1721. So we can say this is minus 0.1721 radian per second, or we can say 0.172 radian per second. We may not take this one. So it is this, and the important thing that we are having a minus sign. So essentially it means what? Essentially it means that after engagement the angular velocity of the system, entire system can be taken as 0.172 radian per second, and it can be taken in the clockwise direction, because you see we have taken everything here anti-clockwise, right? Everything we had taken anti-clockwise. So since our answer is finally turning out with a negative sign, so it means that our assumption is not correct. So after engagement, the angular velocity of the system becomes clockwise, and this will be its magnitude. So let us go straight away into the answer to this problem. What was the problem number here that we had discussed? So it is 3 by 227. So we just see how much will be therefore this answer to this problem. So you see this is turning out to be 0.1721 radian per second clockwise. So they have used this full, this 0.1721, this full value. Anyway, so we see therefore this is going to be my answer. So we see that why we have used this principle of conservation of angular momentum, knowing fully well here that there are some active forces, because we know that there are forces due to gravity. That means if we see here, this will be going to be your force due to gravity. So we can write this is your force due to gravity. This is force due to gravity. Here also there is force due to gravity. So all these forces are acting. This is 6G, this is 4G, right? And then there is also this 2G. This 2G is there, plus we can say this 2G is there, plus 2G is there. So we note that although this system is there, that these are not, you can interpret it in this way as well, that we see here that there is no effective, what is termed as the effective consideration that both these masses are basically equal. And since we can consider it in this way, since there is a large impulsive forces, and this impulsive forces is hidden because we have not exposed this one. Actually there are two approaches to solve this problem. One is termed as the system approach, another is called as the particle approach. So in the particle approach, in some of the problems you may have to do like that. If you do not understand the system approach, sometimes it may be confusing to someone. So under such circumstances, they can use the system particle approach. So in the particle approach, essentially what you can do, instead of considering this entire as assembly as the system, they can take these components individually. What I mean to say is that then you need to take the individual. Here individually means what? Individually means you have the plug and this assembly, correct? So you can take this plug individually and can write it in this way. If you would have followed the particle approach, in that case what you would have done is something like this. This is your, suppose this is your plug, this is your plug and we know that the impulse is basically equal to the change in linear momentum, right? So we can say it is something like this. Since we know 1 I bar 2, we can write it like that. It is equal to delta G bar, correct? And we can write this as G2 minus G1. That means G at time 2. We can say this is G at T2. We can write like this. This is G at T equal to T2. And this is G is T equal to T1. Okay. So we can write this equation in this manner also. I can say 1 I bar 2 plus, right, we can say that it is initial linear momentum G T bar T equal to T1 is basically equal to G bar at T equal to T2. So we can write this equation in this format. Okay. So here we can therefore say that if we suppose that this is our block and we say that this is your, the large impulsive force which is coming, integration dt, okay, and the time gap is epsilon. For a small duration of time this impulsive force is acting, plus to this we add the system's initial linear momentum. You see, this is the impulse plus the initial linear momentum. So we can say that we say this is your plug, and we note that initially this one is having the velocity in this direction. So it is 2 into V2. 2 into V2. What is V2? The V2 that we had already calculated. That this, sorry, this we can say V1, sorry, 2V1. That we had shown that 2V1, so we can say this is 2V1. Change the subscript from 2 to 1. So this is 2V1, okay? So this 2, basically it is equivalent to, this is called sometimes the diagram equation. So in this case, if we do not know, initially since we had taken that all my angular velocities are anti-clockwise. So if that is so, I can say that it should be equal to, this velocity will be now here, and since it is, this will be the velocity. How much will be the velocity? This arm length from here to here, it was how much? This was 0.5 meter. So we can say this is 2 into 0.5 into omega. We can write it in this manner. That means basically it is equal to omega. So therefore, we see from here that our equation gives us like this. If we just take this plug, call all this upward direction as plus, so we can therefore say integration from 0 to epsilon f tilde dt, which is your impulse. We can write this is I bar. We can simply write, say, I tilde. Let's write it I tilde. Is equal to, what happens is that this is equal to omega minus of 2v1. Why it is minus of 2v1? Because you see this is 2v1 in the downward direction. So it is basically I tilde plus minus of 2v1 is this. So I therefore write it in this manner. So it means it is omega plus 2 into V1, and this V1 value has been taken to be equal to how much? This V1 value is 3.431. So we can say this is 2 into 3.431. So we can say this is 2 into 3.431. So that is going to be my first equation. So we say that I tilde, we can write it in this manner. We can say, we can decently write it in this manner. So I get from the first equation, I see that I tilde, correct, is going to be equal to omega plus 2 into 3.431. So we can take this as our first equation. So this is our equation 1. Now I take, because we are doing the particle approach. Please remember, here we are doing the particle approach. Earlier we had taken the system approach. Now we are solving the same problem, because these are the two methods by which you can solve such problems. Either you can go for particle or you can go for the system as a whole. So, and here in the main solution that I had shown earlier, please note that this is the system approach. So we are dealing with this system, and we can write this is system approach. We can say this is system approach. Okay. So this is how we can write it like this. Now what happens with this, that if we go by this particle approach, now I can say that this entire assembly, if you see that again we are dealing with this case. That means let's take, this is the sphere, this is the rod, this is the rod, correct, and we have, this is the plug, I'm sorry, this is the socket, this is the socket. And in this case, there is an impulsive force, F tilde. So we can show this F tilde force directly here. And the impulse of it. That means I can write this is integration from 0 to epsilon F tilde dt. Or I can say this is I tilde. So this I tilde is actually acting in this direction. And there will be some reactions also. These reactions will be also, the impulsive in nature. So this is R tilde dt integration from 0 to epsilon. So this reaction forces will also be, they are what is termed as they are impulsive in nature. Since they are impulsive in nature, and there are certain non-impulsive forces. The non-impulsive forces, of course, is this 6G, and of course this is 4G. Correct. Here also as well we have some non-impulsive forces, but the non-impulsive force, this 2G, this non-impulsive force, its impulse, that means 2G epsilon, right? And here it will be 6G epsilon, this will be 4G epsilon, these will be their impulses. But this we can approximately take it to be equal to 0 when we are dealing with the case when we have both impulsive force and this non-impulsive force. So we can take this impulse to be equal to 0. So here also they will be taken to be equal to 0, and here also they will be taken to be equal to 0. So only we have this case. Plus to it we need to add the initial momentum of the system, correct? Initial linear momentum of the system. So we can say this is your sphere, right? This was your pivot point, and this was your plug. Socket. This was your socket. And at that position, you see your initial angular velocity was provided. This was your initial angular velocity, omega 0. This was your initial angular velocity, which is omega 0 equal to 2 radian per second. So quite naturally, therefore, here the momentum will be what? So we can say the momentum will be what? Here we can write, this was I think it was how much? This was actually 0.3 meter, I think. This distance was 0.3 meter, I think. This is okay. This is 0.3 and this is 0.5. So these distances are 0.3 and 0.5. So we can therefore say that it is 0.3 meter from here. So we can say therefore that because of this anti-clockwise velocity, this is going to be equal to 6 into 0.3 into 2. So that is 0.3 into 2 is the velocity of this sphere because omega 0 is 2 radian per second, and this is its linear momentum. Exactly in a similar manner, I can find out the linear momentum of this socket. So how much is the linear momentum of this socket? So it is 4 kg. You remember its mass is 4 kg. So 4 multiplied by 2 into 0.5. So that is its, the linear momentum. And this must be equivalent to, this must be equivalent to, this sphere. This must be equivalent to this sphere and this plug. And we assume that this is rotating with an angular velocity of omega radian per second. So since we assume it like that, so I can say that the momentum associated with the sphere, linear momentum associated with the sphere will be 6 into 0.3 into omega, and this one will be obviously, you see, this one will be obviously 4 into, this one will be obviously 4 into 0.5 into omega. That is will be your linear momentum of the system. So you see, we have dismembered the system, and we have the plug, and we have this assembly. Okay, so now you see here, this is a diagrammatic equation, and in this equation the only undesirable unknown is this one. So therefore, what we take, this point, you remember, is defined as point O. So this was point O, this was point O. So therefore, in order to eliminate this undesired unknown, I take the moment of everything on the left hand side as well as on the right hand side, moment of everything with respect to point O. Remembering all these impulses are 0. Correct? So as a result, I can say, I can write from this, I can say that it is minus, because the moment is here in the moment of the linear impulse, which is basically the angular impulse, it is in the negative direction because it is clockwise. This vector is downward, this red vector. So this distance is 0.5. So I can therefore say minus 0.5 I tilde. This is minus 0.5 I tilde plus, that means I take the anti-clockwise direction plus. So here everything will be therefore plus. So this will be 6 into 0.3 square, correct, into 2, plus it will be 4 into 2 into 0.5 square. Okay, this is impulse plus initial angular moment of the linear momentum. That means this is angular momentum. This is the moment of linear moment, linear impulse means this is angular impulse. Please note, this is angular impulse. So this is your angular impulse, correct? So this is your angular impulse plus this should be equal to, we can write this should be equal to, assuming anti-clockwise direction as plus, I say that it is equal to 6 into 0.3 square plus this is 4 into 0.5 square whole into omega. So that is going to be my second equation. So this is going to be my second equation. So I can write this is our second equation. So one thing that we need to do is therefore to eliminate this I tilde. So what I will do, I will simply multiply it by 0.5, right, and add these two equations. So I write it will be 0.5 I tilde is equal to, this will be 0.5 omega plus this will be 0.5 into 2 means it will be again 1. So it will be 3.431. Okay. So I now add these two equations. So adding these two equations means that your 0.5 I tilde gets cancelled, which is the undesired unknown. So therefore I can say from here, I just add these two. So I just add this to here. So I get therefore this is becoming, we see from here that it is turning out to be equal to how much? This is F tilde, okay, minus 0.5, okay, fine. So we have to it, I add, this is 6 into, I add these two equations. So I adding these two equations means that it will be 6 into 0.3 square into 2, okay, plus this is 4 into 2, sorry, 4 into 2, 4 into 2 into 0.5 square minus 3.431. Just check, we are adding these two. So it is minus 0.431 3.431 should be equal to this 6 into 0.3 square plus, plus 4 into 0.5 square, right? And then to it we need to add 0.5 whole into omega. So ultimately the equation that I get is something like this. We can say that it will be this we can write, it will be the omega that will be equal to, we can say this is 6 into 0.3 square into 2 plus it is 4 into 2 into 0.5 square minus 3.431 divided by, this turns out to be as 6 into 0.3 square plus 4 into 0.5 square plus 0.5. So if you check this sum, this will be 6 into 0.3 square into 2 plus 4 into 2 into 0.5 square is equal to minus 3.431. The result is minus 0.351. So we say this is minus 0.351 divided by, this is 6 into 0.3 square plus 4 into 0.5 square plus this is 0.5. So it is 2.04. So the result will be, again, take the reciprocal, multiply it by 0.351 and it is turning out to be as minus 0.1721 radian per second. So once again we establish that omega becomes equal to 0.1721 radian per second and the rotation is in the clockwise direction. So you see, therefore, the same problem I solved by two methods. One by what is called the system approach, and the other we call it as the particle approach. That means both ways if you do, this is something elaborate, but you can understand the basic mechanics related that is being related here. The system approach, sometimes the basic mechanics gets masked. It becomes hidden into your system, right? It becomes hidden into your system. So you can solve any problem by the system approach, but sometimes, as I am telling, system approach sometimes may be confusing. So in that case, although the particle approach takes little longer time because it's an elaborate process, but definitely it is error free. That means if you ritually draw your figures, and remember, particularly you should remember the vector sense, because lot of vectors are involved into the situation here. So lot of vectors are there. So if you actually give attention to these vector approaches of various quantities which are involved into the system, you will be peacefully coming out and successfully will come out with your equations. Although the basic demerit of this process is that it is a certain little bit lengthy process. It takes certain time, but it is of course the error free, and also you can explain all the hidden principles of dynamics that we have here applied. So students, I therefore expect that after going through these two examples, which I have solved in detail, and focusing on the different aspects of the solutions, so you see you should be able to solve your similar types of problems in from the book. So with this, basically we come to an end to the subject of to the chapter of what is called the impulse and momentum and its equivalence principle. And of course, in the next chapter, when we will be taking up, we will actually, take up the more general discussion of the dynamics of system of particles. Till then, it's bye from my end, and thank you.